All right, here we go.
Thanks everyone for joining for the second talk in this session. I'm really delighted to be able to introduce our next speaker, Rahul Bhadani, who's a PhD candidate at the University of Arizona, and he's been working on modeling and simulation of vehicle controllers for mixed autonomy for the last few years. Today, he's going to talk about his work on scalable simulation frameworks and what does it take to deploy vehicle control from mathematical models or computer models into hardware. Rahul, go ahead and share your screen. And if you have any questions that you want to make sure get covered as an audience member, send them to me in the chat as the talk is going on, or we can have them at the end. Rahul, please take it away.
Hello, everyone. It's nice to be here and welcome. Today, I'm going to talk about some of my work. First part of the talk is related to a scalable simulation and how you can have a repeatable and scalable simulation in 3D environment. And then second part will be related to the development that how controller for the mixed autonomy go from mathematics and to computer, and then how we deploy it in the hardware. So you already have seen, I'm pretty sure like 1,000 times this controller video, and Professor Bayan also demonstrated this video, and Dan talked a little bit about that. But it's not just the experiment that we got out of out of nothing. We had a lot of engineering work that we put together to making sure that everything will work nice and there is no any issues with that. So this talk is like a story about how we got to that point and what were the things that were required for this kind of experiment to perform, and the one that we did in Vanderbilt this past summer. So like we have a controller in mathematics or as an algorithm. Now, the point is that we want to test it before we can go to the field experiment, because the field experiment is expensive, logistically challenging. It requires so much of the man hours and manpower. And so the ideal condition is that, let's say first we are going to test in the simulator. But also at the same time, ideally we should expect that the result that we get in the simulator should match the result we expect to get in the field with real vehicles. Does this happen? So the question is that, does this happen? So we will answer that question in a while. But how do we do in the simulation? So we already saw in some previous talks that there are micro simulations that make it work with thousands of the vehicles, hundreds of the vehicles. But there are challenges with that as well, because they're not the 3D environment, and the real life is a 3D scenario. And they don't per se simulate the sensor statistics. There is also a lack of inter-vehicle communication in those kind of simulators. So we have some other options, like say, for example, ROS and Gazebo. Some of the new generation of the simulator recently came out. And so these kind of the simulators do the sensor-enabled environment sensing, real-time message exchange. And also we can plug some hardware along with the simulation so that we can do some of the things that it's hard to model in the simulation. And so for the Arizona Ring Road experiment, we had the settings like say, where we had one car that had a front laser mounted, that was a 2D LiDAR, as you can see on the top right. And it was following a vehicle that was a human driven. And there was no, in the realistic field settings, there was no inter-vehicle communication in that sense. So we had to estimate the leader vehicle's positions as well as its relative velocity that was required for mixed autonomy velocity control. And so for those kind of the controls, when we deploy it to the real vehicles or even in the simulator, the state of the art approach currently is a robot operating system. It's currently one of the most popular middleware framework that allows to control any kind of autonomous systems, whether it's a drone, autonomous robots, autonomous vehicles, industrial robots, or your Roomba vacuum cleaner, anything like that works on the ROS. Then we also have other kind of the simulator, next generation simulators that came out, like say, for example, Carla, Air Sim and LG Simulator. So these have been recently come out in last 2-3 years. And so when we talk about like a vehicle control development, the kind of the controls with lots of mathematical formulations that Alex Keimer and Shawching talked about, those kind of mathematical formulations, they're not just enough. We also need to translate into the computer program that eventually our intention is to deploy into the hardware. And though if you're going to code that kind of controllers with so many conditions, realistic behavior that we want to have, then we have naturally we are going to write a code. But those kind of writing code actually is a tedious and turnaround time is really large. So we can also resort to some of the newer approaches in software engineering methods that we call model-based design for controller development. So what's the idea behind it? That somebody else has developed already like a pre-made blocks that has been thoroughly verified and tested for one particular kind of the task. And then what model-based design does is that you can bring together all those pre-made blocks, put together, write your algorithm, and then you can generate hardware deployable code. And so MATLAB actually has one such kind of feature now by the virtue of the Simulink and robotic system toolbox. And that lets you generate a code that you can either run in the simulation or you can also directly deploy into the hardware. And at that point of time, there is no change in the code required. So if you know that that things have worked in the simulation really well, then you expect that there should not be any issues in terms of the integration and the deployment. And so how do we verify the controller behavior is also a big question, because mathematics is good, but we also want to have the real life statistics, real world statistics. And so a couple of things that we do, but the first thing that we care about in our field is safety. We don't want to crash the vehicles, crash into each other. And then the second is that since we are the main concern for the mixed autonomy project is that whether we are able to dissipate the traffic waves or not. And so to check whether the controller is unnecessarily leaving a large space gap or not. And then is the controller sensitive to vehicle dynamics? Because depending on how the different vehicles behave, either in the simulation or with the real vehicle, the controller itself might behave very differently because we have the feedback control. Then how these vehicle dynamics, how these controllers react to the sensor noise. Do we have an estimation problem? Like say, for example, in Arizona Ring Road experiment, we did not have any inter-vehicle communication, and we also did not have any high fidelity data to estimate the position and the relative velocity of the leader vehicle. So we have to write some estimation algorithm. So how does the controller behaves when we have this kind of issue? The second is the data rate and the time step, because not all of the signals come at the same rate, and they also don't have a uniform sampling time. So these are the practical challenges that usually do not occur when we are formulating our controller just as an equation. And so for that, we have some of the testing methodology, like the software in the loop simulation, that we test everything first in the simulation and analyze the result, whether this is meeting our expectations. Then we also do something related to the hardware in the loop testing, where say we deploy the controller in one vehicle, we test with some ghost vehicle, say for example, as was done in a CAN coach experiment described by Dan earlier. Also, we can have realistic sensors, like say for example, some new kind of the sensor that we are hoping to deploy into the car, but there is no equivalent sensor in the simulation. So we can plug with the simulated vehicles and the real sensor, and then we can study that. So how good is the simulation? Now, go back to the earlier question that I asked, that can we trust the simulation, and how good is the simulation in assessing the performance of the controller before we can go to the field? And so the one issue that we have found out during the Arizona Ring Road experiment controller development, that we cannot trust simulations all the time because it lacks the repeatability issue. It lacks the repeatability. For example, you can see that I had two simulations running on a two different computer, left and right, and it's just an open loop control, and the vehicle is tracing a circle. And so if you plot an x positions on the on the graph with respect to time, then you will expect some sinusoidal waves. But you see that when I plotted for the x positions of the car, basically it is not the same, and it actually drifts apart a little bit. And the same simulation on two different machines also does not come out to be the exactly same. So we have a repeatability issues in this manner. And so if somebody is testing their controller on one machine and somebody else is testing on another machine, so like a very high performance computer, then the results might turn out to be significantly different. And if the controller has been running for like an extended period of time, the result also might diverge. And so this is a metrics that I calculated, like say how the trajectory of the two simulations vary. So with the time, you can see that the error, the quantified as a root mean square error of the trajectory, basically diverges over the time. And so which is bad, because for the sake of the reproducibility of the research as well, we want our simulations to be reproducible to as large extent as possible. And then the second issue that comes out to with this 3D simulation, the physics based realistic 3D simulation, is the scaling. In 3D simulations, we try to emulate like the rigid body dynamics with collision detections. And there is also like the joints of the different parts that is also simulated. And then we have a ray casting. Ray casting itself is extremely computationally expensive. Then we also have a message exchanges that occurs over the TCP protocol within the same computer by the internal mechanism, or between the computers on the network. And so this overall process is extremely computationally expensive. And further, when we try to add more costs to the system, then also system starts slowing down. And so these 3D simulations are also built in a way that this will try to give the result as fast as possible, but also at the same time as accurate as possible. So there is a trade-off there between giving the result accurate as possible and fast as possible. So to make that happen, the simulation at 3D simulators actually slows down itself a bit so that it can make the computation possible and then give back the result. However, these are stochastic, and depending on your computer load, these might not be the same when you run the simulation the second time or third time. So we tried also to simulate the 22 cars in ROS and Gazebo. Gazebo is a 3D simulation framework powered by ROS. And so the physics itself, the rules of the physics here was not obeyed, because the system load is so much in that case that it cannot take that many number of the messages coming from each car. So in that case, each car is producing its velocity, the relative velocity of the car, distance between the two vehicles, then the joint states, and the number of other parameters, because we are also simulating the sensors in this case. And so you can see that like the vehicles are stopping down, it does not stay on the course. And this is not because of this controller is bad, but the simulation is not behaving well when we have this many cars. And so this is like a real-time factor I plotted over the time for different number of the cars on the Gazebo simulator. And so we have a one car. So one car, you can for the one car, the real time factor was 1. So it ran for a couple of seconds, like maybe 40 60 seconds. Then 4 cars, and they are overlapping on each other, so you cannot basically distinguish. But as I increase the number of cars, you can see that the real time factor it starts slowing down, and they are stochastic. It's not like that every time you will have 18 cars, then you will see this light red color curve, or if you have a 20 car, then you will see exactly this kind of the curve. It will vary every time you will run the same simulation. And so this actually sacrifices the repeatability as well as sacrifices the scalability, because we don't know what's going to be the result when we run the simulator next time. And so we can test these kind of the controllers on 2 cars or 4 cars, but constructing whole lot of the traffic is again another kind of the problem. But when we are dealing with a controller that's going to the mixed traffic autonomy, we need a lot more number of the cars, especially if we are also relying on something like a sensors to make an estimations about some other state parameters. And so the pain point here is that we have too many messages to exchange when we have a large simulations, and then there is synchronization issue at the larger scale. How you're going to synchronize all the messages so that all the vehicles receive update at the same time, so that we expect the determinism of the simulation. And then there is a lack of repeatability, so that sacrifices the reproducibility of our results. So some of the simple method that does not require to change the existing software itself is that we have worked on. So one thing is we can throttle down the message rate to the system load, and we can explicitly simulate at a slower than real-time factor. So if you see this, say for example, in this curve, if to simulate the 20 cars, how about if I keep the real-time factor explicitly at 0.2? So it's less than what was permissible by, or what was given by the simulator at that time when I was running 20 cars. So then we can also create some algorithm to synchronize the agents that's we call director node. So that will allow you to have update the positions or state of the vehicles in a synchronized fashion. And then it turns out that we also don't need to simulate the realistic physics, the rigid body dynamics in the simulator. So we can use something called as a federated modeling approach, where the actual dynamics of the vehicles can be simulated out of the 3D environment, and we can just propagate the state update to the 3D environment. And so that way, the computational load on the 3D simulations will reduce a lot. And so if you look how the simulation is currently done, that does not allow to do the reproducibility, is that we have some control algorithm that we wrote in ROS. Then we are connecting with a 3D simulation where the vehicle dynamics is within the simulation, and that's actually simulating the rigid body dynamics. We have a sensors, and then it does the feedback loop, and then gives you the output, and then we have some system gain, and then back to the feedback. So this is how it is done. What we are going to propose is that this vehicle dynamics part comes out of the 3D simulator, and we do it as a standalone program, a standalone node. And then we have a director node that will synchronize the state updates, and that gets propagated to have an update, change the state updates in the 3D simulator. But note that still by this method, we are still going to do the sensor simulation inside the 3D simulation, because we want to simulate the sensor to emulate the real world. And one proof of concept, what I did was that just design a bicycle model for the longitudinal dynamics of the car instead of the real rigid body dynamics, and let it simulate the car. And then we implement the controller with that. And this is like a mechanism for the update director node, that how we are going to synchronize the state update, that let's propagate the updated state all at once to the gazebo physics engine, our 3D simulator. And so why also why the director node is required to synchronize. So each agent updates at say T1 time, T2 time, but even the update gap, the update rate is same, but not all of them got executed exactly at the same time. And so you will see that, like say for example, in the simulation, the leader vehicle's position has changed at time that is not synchronized with the um, position change of the ego vehicle. So in that case, you will see an abrupt jump of the distance as measured by the laser, the simulated laser sensor. So that will actually introduce an spurious relative velocity estimation that comes out suddenly because of the asynchronous state update. So that's why we need synchronization. And so with this method, I just had 2 car simulations that you keep doing it in a circle, and then it comes out to be the same with a slight bit of the difference, because still it's not exact, but we are able to achieve the repeatability to the much larger extent. And for this, since it's the 2 vehicles, so we set the desired real time factor to be 1. So it's the wall clock time and the simulated clock time is exactly same. And so this is like a comparison with the old methods that has been going on in ROS and the one with a federated architecture. So you can see that both those methods, that 2 are very different. Then we also now, by setting the real time factor as exactly as 1, we first tried with that many number of the vehicles, and the state update was throttled at 20 hertz, so that once every 1/20th of the second, state update of the vehicle is going to be changed. So in this case, we still got the deterioration in the real time factor. And so the idea from now onwards, I know that I cannot simulate it at the real time factor of the 1. So let's explicitly simulate at a much lower real time factor. And so this one was simulated at a real time factor of the 1. And this actually runs also very nicely, and almost like the repeatability is achieved in this case. So the next slide, maybe have a plot. Okay, so this is the metrics for the repeatability. So like say, for example, I had 2 machines, slow machine and fast machine. Like slow machine as like it has a less amount of the RAM, weaker processor, fast machine, more amount of RAM and better processor. And so, so like we have the 4 simulation, 2 run on the 2 using the old kind of the method, which where repeatability is, there is an issue with repeatability, and the one where there is an issue with, and the one that we try to solve the repeatability issues. So you can see that the root mean square error for the trajectory deviation, we were able to like bring it down much lower as compared to the old methods. So now, is this enough? Like we done with the simulations, like we have the very good simulation, all the repeatable and scalable simulations. So is this enough? The question is that, like, maybe not. Why? Because we are still not doing we don't have a real data, especially when it comes to like the trajectory data. The car following model is good, but there is still not the same as like the how human drives on say I-24. So for that, if you consider that we already have those data that comes, we can get like out of nothing. We don't have to do much. We already have a vehicles onboard sensor on the vehicles. We can also have an augmented LiDAR sensor. We just need to mount it. And then we can have a dash cam. We can also have a roadside infrastructure, roadside unit if we decide to have a V2X communication. And so this leads to the next step, something called as a data-driven approach for the vehicle control. And so this is just an architecture that we have a CAN bus on the car, and we just need to know how to harness those CAN buses to retrieve the vehicle data. And for that, we tried to develop a custom code for harnessing the CAN bus messages using the comma.ai Panda devices. And most of this work was done by Matt Bunting, who is also a postdoc at University of Arizona working on the Circles project. And so he developed a hardware driver for CAN bus data that we can retrieve from the CAN bus messages from the car in the real time using the Raspberry Pi. That's a small computer that we can plug it into any car. So that comes out as like a cheap or like a low cost ways to harness the CAN bus messages. And so another question is how to make sense of these data. So the CAN bus messages comes out in this format that we have a time and the bus and each message ID corresponding to one particular signal. And then messages are coded as hex messages. Along with that, we also can get a GPS data, and that we can use it for like ground truthing to check where the vehicle is, and many other things like, say, for example, estimations of the road grade, if like, say, for example, if we have a really high fidelity data.
Just want to flag
So
the
for
time.
that,
maybe take 2 or 3 more minutes so that we can try to end roughly on time.
Okay. Yeah. So for that, we developed something called as a Python package to analyze and decode the data so that we can use it for the data-driven control. And so in this case, like we have a number of the different signals, and then we can operate on that to make sense of what's going on, make some inferences. So just to go back to the main couple of main highlights is that how we deployed it. So that we have the Raspberry Pi with the libpanda, the custom hardware, and then we get the data, and then we can decode using the stream. And so this is important for the controller development so that we can get a realistic trajectories. And so skipping back to the some of the why the realistic trajectory is important is because we also want to develop the controller that is not that's not having an issue of the naive estimation. So we can get some trajectory, and then we can compare with that how we are going to develop estimation algorithm to develop some states that is not available. So if we have a bad estimations, then we can get a really bad control behavior, as you can see from the phase space plot of the follower stopper. However, if we do the estimations well, then our control command is also very smooth, and we are not going to get unrealistic control behavior. The second, how we did, we validated the controller using the transfer test is that we develop everything in the Simulink model, and then we generate the control code, which was already tested with the simulation framework. Then we did with a ghost car approach, that the leader vehicle is a ghost car that's like in the simulation, but actual vehicle is following that. Then we gather the data, and then we look at the data to see like how the controller did. And so in this case, similarly we also tried to test the number of the machine learning based controller, like how did they behave in terms of the transfer test for coming from a trained in a one kind of environment called as a micro simulator, Sumo or MSUM, and then we test it in the field. And finally, to deploy those kind of the machine learning controller, we translated the trained model into the ONNX format that was used to generate ROS code, and that ROS code was used to deploy on the real vehicle. And so this for translating the command, we also had something called as a ROS CAN integration, which using the ROS to CAN package, which was primarily developed by SAF1. And so using that, we were able to actually control the command and control the car in the vendor test last summer. And so this is like the testing, like how we did with a number of the different cars. Okay, so that's all. Sorry, we had to rush at the end. So this whole work was funded by National Science Foundation and Department of Energy, and all thanks to a number of people who made this test possible. So any question?
Thanks, Rahul. If you have a question, either throw it into the chat if you'd like for me to ask it, Or if you want to just jump in, please jump in or raise your hand, and I'll be happy to help to navigate that. I think we're maybe just a few minutes over now, but I don't think we got started exactly at the top of the hour either before. And so I know we have a break coming up. And so if you want to stay on and chat with Rahul a little bit during that break, I think that would be fine. But Marie, should we take a few minutes for questions now to just have it, or should we just have like an informal gathering of folks who could stay for a few more minutes?
Yeah, maybe. Okay, maybe we could have a question like just like a few more, just a few minutes, and then we'll have the 1 hour break anyway. So if it's 55 minutes, I guess.
I have a question, Rahul. So about the reproducibility, right? Reproducibility is important, but if you have something that has some randomness, and when you run it twice or three times, you get a different answer, then you get a framework that makes it always give the same answer. That is still not good if the answer is wrong, right? So, so the first question is, of course, that sometimes one could argue that having some randomness and how different they are from run to run could help you get some idea. But the main point is, it really matters what the nature of your simulated system is, right? Specifically, is the state that you're simulating dynamically stable or dynamically unstable? So if we think of the ring road, right, and you have a stable system, then obviously you want always the same answer. But one could argue that if you have a system where you want the wave to develop, right, and become unstable, then you actually want your simulation to have some randomness, some uncertainty, that it triggers these things. Now, to be clear, the what you call stochastic in gazebo was not physically correct, right? What would be perturbations in reality? But one could throw in that in many applications, you actually do want some physically reasonable model of noise in some sense added. So that's sort of, I think, an important perspective to keep in mind what it means to have a reproducible simulation. What would be your comments on that?
Yeah, so you have raised a lot of good points on that part. And so my work is when it comes to the like having a repeatable or reproducible simulation is not removing the randomness or perturbation of the dynamics of the system, but perturbation or dynamics or uncertainty that comes because the simulator itself is not able to handle that many messages, that complex rigid body dynamics. So and so that's why the main point here is that we can think that the dynamics of the vehicle, that we federated it outside the gazebo model, that itself you can choose to be any arbitrary dynamics, and that can have an inbuilt some stochastic behavior, and then that lets you propagate the state updates to the 3D simulator. So that way we will still be able to do some stochasticity into the simulation, but that will then not be caused by things that you do not have control over. Basically, like we are not aiming to rewrite the gazebo software here or the ROS software. So that's why the federated model comes into the picture. And so because of that, what you said, it will still be valid, that we can have a stochasticity. And also we are also emulating sensors into the gazebo using the ROS C++ code. And that has some statistics, like a sensor statistics, like you can have a Gaussian, Poisson, etc. So that way we will still be able to get something that may correlate with something real world.
Excellent. So let's all thank our speaker. And if you're interested to stay and ask a couple more questions, I think we have some space coming up now. If you want to switch off the recording.